this webinar now, and welcome to the second YAPSE webinar with the title From Quality Control to Decision Making on the Management of Bridges and Structures. What's next? So my name is Paul Linnenberg, and I'm a Chief Specialist at Incovi's headquarters in Denmark. I'm employed in the Department of Operation and Maintenance of Bridges, and I'm very glad to be moderating this session. I'm also the chair of YAPSE Task Group 5.4 on Structural Management System, and I'll be moderating this session where Jose Matos will give his presentation. First, I will mention a few practicalities. All participants have had their microphone muted, but it's possible to, after Jose has given his presentation, to post questions with the question and answering Q&A button below this Zoom webinar tool. I will present a brief introduction and then followed by a roughly 40 minutes talk by Mr. Jose Matos, and we will have a Q&A session, and we will aim at finalizing this webinar at 3:15 CET. That's of course dependent on the number of questions, and please keep them in writing. We are hosting this live in Zoom and on YAPSE Facebook, and this webinar will be recorded and uploaded to the YAPSE webpage afterwards. First of all, I would like to thank YAPSE for hosting this webinar. It's an excellent opportunity to be discussing this issue and for organizing it all. I would like to present just a brief introduction by PowerPoint here. So I will share my screen. So here it goes. This is the title, From Quality Control to Decision Making on Management of Bridges and Structures. What's next? And I have given a presentation of Jose Matos and myself. So a few words about YAPSE. It's an international association for bridge and structural engineering. It's a scientific and technical association comprising 100 countries and counting 56 national groups worldwide. It was founded in 1929 and it has its headquarters in Zurich, Switzerland. And YAPSE deals with all aspects of structural engineering. So it's planning, designing, construction, operation and monitoring, and inspection, maintenance, rehabilitation and preservation, demolition and dismantling of structures, taking into consideration the technical, economical, environment, aesthetics, and social aspects. So it is the last items that we will talk about here today about the management of bridges and structures. And YAPSE names structures that include bridges, buildings, and all types of civil engineering structures. I'm sure that Jose will also touch upon that in his presentation. YAPSE's mission, the aim of the association is to exchange knowledge and to advance the practice of structural engineering worldwide in the service of the profession and the society. And for this purpose, YAPSE organizes conferences worldwide. It publishes the high-quality journal SEI. It publishes books reflecting the works of all the technical groups. It creates technical groups as required by the need and the technological progress. It offers the possibility to join activities within natural groups of YAPSE, and it offers programs for young engineers, and it presents some annual awards. And this webinar fits nicely into this. I would like to pay attention to YAPSE's Commission 5, which both Jose Matos and I is heavily involved with. So YAPSE Commission 5 is on existing structures. It is headed by Rade Hadjian from Switzerland, and it deals with all the issues, or many issues related to existing structures. So it is, you can see on the right side of this presentation, the current task groups of Commission 5. So it's 5.1 on forensic structural engineering, chaired by John Dunderman from the US. We have the second task group is on key performance indicators, and is headed by José Matos of Portugal. We have task group 5.3 on diagnostics, headed by Jan Gen of Poland. Then we have the fourth task group on structural management systems, which is chaired by myself. And we have the fifth task group on conservation and seismic strengthening and retrofitting of existing masonry structures, and is headed by Andreas Lampopoulos from the UK. And then I should also mention that we have a new task group on resilience that's just starting up, and there's a plan to have a task group also on BIM, which is very relevant also for existing structures. So you can see Commission 5 has a broad range of activities within existing structures. And I will just briefly present the three task groups that you can actually see on the YAPSE webpage. It's the task group 5.2 on key performance indicators. As I mentioned, this is today's speaker that is chairing that. And you can see it's about key performance indicators and how to assess these and etc. José Matos will for sure give us a good introduction to this. And then there's the fourth task group on the structural management system, where we do a survey on implemented best practice and also on the promising research, and we will try to address if there's a gap and how to progress the industry from latest knowledge within structural management systems and decision-making models. And then there's the fifth task group, which is on the seismic strengthening and retrofitting of existing unreinforced masonry structures, headed by Andreas Lampopoulos. And he has made the first YAPSE webinar, which is available when you go to the YAPSE webpage, and in a section called e-learning, and there you will see a great presentation with the Q&A session afterwards, where you can learn a lot about this subject. Now today's speaker, that is Mr. José Matos from Portugal. I'll just give a brief bio of him. He has received his PhD in civil engineering in 2013 in the field of probabilistic-based safety assessment of existing structures. He is teaching and supervising master students and PhDs since 2007 at the School of Engineering at the University of Minho. He is a member of ISE, is the Institute for Sustainability and Innovation in Structural Engineering. His research fields are bridge engineering, asset management systems, life cycle cost, safety assessment, risk evaluation, and sustainability. I guess that all of our participants at today's webinar can see that these items are to our interest. He is also a co-author of more than 100 publications, international conferences, and journals. He participates in several international committees and coordinating international working groups. He's also involved in coordinating of several international and national research and development funded projects. He has been chair of the Cost Action TU 1406 on quality specifications for roadway bridges, standardization at a European level, which has been recently completed. And more recently, he was elected as president of Eurostruct and is a vice president of IAPSE. So with this brief introduction, I would like to give the floor to you, Jose, and we look forward to hear your presentation, and then we will do a question and answering session afterwards. Thank you very much.
Thank you, Paul. I hope you can hear me well. I'm going to share my screen now with everybody. And I also hope you can see, I also hope that you can see my screen. It's a pleasure to be with you today and speak also about these topics. because they are very relevant topics that are being discussed in many projects that my research group is involved. And in this line, I would like to acknowledge IAPSE for the invitation that was made, and also to all the colleagues that are belong to this group and that supported me on the development of this interesting presentation that I'm going to make today. So, the outline of the presentation, I'll start with a brief introduction about the situation point that we are living today in terms of management of bridges and structures, and the need of efficient tools for a better management of these infrastructures or bridges and structures. Then I'm going to give you a brief overview of quality control framework that was discussed and established on a previous cost action that I had opportunity to share, and that this framework is now being extended to many other kind of infrastructures. Then I'm going to give an example on how we can go from the quality control to the decision making, or how quality control can be useful for decision making, or in other way around is how decision making can be part of quality control, because at the end they should be part of quality control. And to finalize the talk today, I'm going to give you some overview of what should be the next steps for a better management of bridges and structures. So take into account the quality control procedures and the decision making, what will be the next steps. So in engineering, quality control is related to systems development in order to ensure that the products or the service met or exceeded the expectations and need of users and community. This is the definition of quality control. And when we go to bridges and structures, we must say that asset management, that all of you are aware, and quality control, they are the two sides of the same coin. However, there is an increasing need of developing strategies in order to ensure the quality of the entire system, and with the same, or with the aim of reducing risk of unexpected costs. So that's the reason why we want to do better quality control, and in line with that, more efficient asset management. We know today that many bridges and structures are approaching the end of its lifetime, and these make these bridges and structures critical assets in order to ensure the mobility of people and goods. And we all know, for instance, the situation of the bridge in Genoa, that the costs of the collapse were not so the cost of the collapse directly cost, but also was the cost of the collapse plus the cost that has the impact on the economy and on the society of the period that the bridge was unavailable for everybody. Also, we know that some structures shows a faster deterioration process, mainly due to a poor design and construction that we know that during the design process and construction process, the quality check was not so good. And these structures, they shows faster deterioration. And also this deterioration process is accelerated by external factors, such as the increase on the traffic demands, or also due to natural or man-made hazards that we all know today that are facing our infrastructures. So we need to establish maintenance actions in order to make those structures more efficient and more with a higher performance, at least during a higher period of time. And in order to do that, we need to take efficient decisions based on an optimized plan of interventions, and such interventions should be made in order to keep the structures as functional as possible. So this enters into what we call as the life cycle approaches. And on life cycle approaches, we need to take into account the economy of costs, the costs that we have from the operation and using of these infrastructures. The social costs and the social part also, because we have an impact due to the availability of the infrastructure and so on. We have an impact on the people, the society, and also the environmental cost, which is something that is more recent, but we need to also take this more and more into account. So the definition of an holistic and integrated approach for life cycle management of bridges and structures becomes crucial. And this approach should have into consideration the condition inspection and monitoring, should have into consideration a good performance assessment and modeling, also the interventions that we need to implement, and also the standardization of best practice on the maintenance and management of those structures. Thus, there is a need for an harmonization of different standards and codes into the definition of new guidelines for lifetime extension. Now, I'm going to give you an overview of what is a quality control framework that was decided and discussed within the cost action 1406, which is a cost action that was shared by myself, but with a collaboration from colleagues from all over Europe. And you can go to the website of this action, and there you're going to have much more information about the framework and the quality control framework that we are implementing and we developed and proposed during this action. So as I said, we know that we need to assess bridges. This assessment is mostly made through visual inspection procedures. We all know that. In some occasions, we use NGT tests. And in some specific situations, we can implement monitoring systems, permanent or temporary monitoring systems. The good thing is that all of these will give us an indicator that gives us the performance of our bridges, of our infrastructures during their lifetime. Of course, most of this indicator is visual based, so very subjective and depending on the technician that is doing the inspection. But more and more we are starting to have indicators which are more objective and based or calculated or obtained through more efficient techniques such as NDT or monitoring. Then we need, based on these indicators, we need to check if the infrastructure, if the bridge is accomplishing or not the goals for which it was designed. So it is or it is not. And this checking, if it is or not accomplishing the goals, is made through a quality control plan. And this checking should be developed during the whole time of the bridge. So what is performance indicator? And this is a very important definition because performance indicator is the base of everything. And it's something that you can measure or quantify, a parameter that you can measure or quantify, related in this case to the bridge performance, but can be related to any kind of structure performance that can be compared with a target measure of a performance goal that can be compared with a goal or can be used also for ranking purposes. If we have a stock of bridges or stock of structures, similar structures, we can establish ranking and take decisions based on performance indicators. And this is made under a quality control plan or a life cycle management procedure. So you have here in this image below explanation of indicators, performance indicators that we may have or we may obtain for each bridge, for each structure, and also a connection between these indicators and the goals that we want to achieve for each bridge. And the goals should be minimize the owner cost, should be minimize the user delay costs, or in other way, maximize the availability of our bridge, should be minimize the environmental costs, the impact, environmental impact, and keep our bridge and our network safe for the users and reliable as it's. So this is part of the decision-making problem. We have different scenarios. From each scenario, you can have different indicators, different values, and this will allow us to know whether or not we are going to achieve the goals for which we design and we build our bridges and our infrastructures. So we can connect those goals with what we call as a KPIs, or key performance indicators, because they are key, because with these key indicators, we can do the decision making. We can establish and identify the most alternatives and the most fruitful scenarios for each situation that we have. So we identify from different key performance indicators, and I'm going to explain this a bit more. We identified the economic, availability, environmental friendliness, and reliability and safety as the most important ones, in this case for bridge structures. So this is the KPIs, the key performance indicators that came from the Dutch Ramship approach. And we decided during this cost action, as I told before, that for bridges, those key performance indicators that are indicated in red color are those that are really relevant for the decision-making procedure. And those that are in red color, we can include the reliability. And when we speak about reliability, I believe all of you are aware of that, at least those that are from the structural engineering side. Reliability is directly related with the safety or the serviceability of the structure. So it's something connected, directly connected to the structure itself. Then we have the availability. The availability is connected to the operation of this structure, how this bridge is available or not to the traffic. Is it in operation for the users or not? And this is the concept of the availability KPI. Economic, we all know what is economic. It's the costs that we have costs with interventions and the maintenance of our bridges. These are the economics KPI. And then the last one is safety. Safety is nothing related with the structure, is related with the harm people that can be harmed during the service life of the bridge. So in other way, it's related with the loss of life and limb due to structural failure. But during the structural operation. So not related with the structural failure, but related with operation. Let's give you an example. Imagine that you are driving a car and you have an accident. And then you shock with the safety guards. If the safety guards are not in a good condition, you can fall down from the bridge. This is the safety of the bridge to the users. So nothing related with the structural part. However, if we speak about reliability, for instance, we speak about the collapse of the bridge due to bending or shear failure. Or we can speak about the maximum displacement or the vibration on the bridge. This is related with the serviceability. So this is reliability. Safety is how the bridge is safe for the users. Then availability is how the bridge is in operation for the users, and economic is the cost. There was a discussion about including or not environmental friendliness, how environmental friendliness are our interventions. And this was discussed among the cost action, but at the end we decided not to include because there are still a lot to do in these topics. So we keep with these 4 KPIs that will allow us to take decisions on the best alternatives, the best scenarios for interventions on our bridge stock. So reliability, availability, safety, and economics. And we can split these KPIs in 2 big groups. The first one is what we call of static quality control or snapshot. And why we put the reliability and safety there? Because if we go today to any bridge, we can evaluate the reliability of the bridge in terms of safety or serviceability and ultimate limit states. So we define the performance limit states and we can evaluate and assess the reliability today. And also we can assess the safety of the bridge today to the users. This is something that you can do today if you go to any bridge to the site. Other KPIs we call, and we group them in what we call as the dynamic quality control, because costs and availability, they depend on two things. They depend on the forecasts of the reliability and safety, and this is connected with the degradation model, the deterioration model that we are implementing to do these forecastings. And also they depend on the strategies of interventions that we want to implement on our bridges. Some strategies will have higher costs or higher availability. Other strategies will have less costs or less availability. So with this quality control framework, we can somehow connect the damage process that is governing the deterioration of our bridges with the performance indicators that give us information about the performance of our bridge. And this comes from the observations that we have directly on the bridge, but comes also from other data that you take from the bridge. And once you have this indicator, we have a value for each indicator that we can obtain with visual inspection, with NDT, with monitoring, and we can connect this value with the KPIs. In this case, safety, reliability, availability, and costs. These are the KPIs that will allow us to make decisions. So we can make decisions and get these KPIs and these values for each element of the bridge. For each bridge type, can be a girder, arch, or frame bridge. And for each level of analysis, you can do it for a component like a bearing device, for a bridge system, or for a network of bridges. This is somehow the procedure that I explained before. So we split the KPIs in two levels, the reliability and safety KPIs, and then we go to the bridge, we assess the bridge, we calculate these two KPIs, and then based on the scenarios that we have, we can target different KPIs in terms of availability, in terms of costs, but also we can project the reliability and the safety with time. So we have a multi-criteria decision-making, multi-objective decision-making, where we want to check what is the best scenario, the optimal scenario in terms of interventions, take into account the lifetime of the bridge or the period of analysis, and take into account the KPIs, reliability, availability, economy, and safety. So this is a brief example of explanation. This is a bridge in Serbia. It's a reinforced concrete frame bridge with an average daily traffic of 10,000 vehicles. This bridge was built in 1963, and later it was widened in 1977. So from the design checks and information we get from the design, there was no particular weakness that were identified in the design, so no human errors. There is an obvious weakness on the connection between the old and the new part of the bridge. And also there was no identified any problem on the materials. It was indeed identified increase on the traffic demand from 63 to 77. And that's the reason why we calculate or we recalculate what we call of the prior or the version reliability index, which is the reliability index of the bridge without any damage. We recalculate it for the new traffic load. And the value we got was of 3.8. Also, in order to do that, we need to identify the governing collapse mechanism, the two main mechanisms that can put the bridge in collapse in terms of ultimate limit state, and we identify a bending and a shear collapse mechanism, and consequently, we identify what we call as the vulnerable zones, or the zones that are critical for this bridge. So after doing the analysis of the drawings and so on, we came to the bridge inspection, and we identified some pathologies and also the location where these pathologies were checked. We are speaking about diagonal cracks in a abutment. We are speaking about some corrosion in the conjunction area between the old and the new part of the bridge. We are speaking about some spalling and some corrosion in the deck. And according to the information that we get from the inspection, so spalling at the width of 1.5 meters over the wall span, some significant corrosion on the old structure, some corrosion in the new structure, but in the vulnerable zones, there no probably some corrosion over the piers, based not on what we see, but on the symptoms that we get from the inspection, symptoms from the bridge, and also this diagonal crack due to shear. This is the shake that we get from the inspection that we made from the bridge. And based on experience and some statics, elementary statics, we may say that a resistance reduction of around 10%, probably due to this significant corrosion that was identified, it happening. So the bridge, comparing with the version reliability with the bridge without damage, there is a reduction on the resistance of around 10%. And then we can compute this kind of plots where we correlate the reliability with the probability of failure for the reliability KPI, and also correlate this with the resistance reduction factor for each bridge. So we had an initial reliability of 3.8, and then we identified, based on our experience, a reduction of 10% on the resistance of our bridge. So after or today, with the inspection and the results we have from the inspection, we may say, based on these plots, that the reliability is around 2.9 to 3. So we can also establish different scales for reliability and scales in terms of ultimate or serviceability limit states. These scales is from 1 to 5. 1 means that the bridge is in a very good shape and 5 is a very bad shape. And since here we are speaking on ultimate limit states, we can use this first scale where is a scale based or for the ultimate limit states for the collapse mechanism of the bridge. So based on these values that are values given us from the codes, from Eurocode and other codes, we can establish these 5 scales. And based on these 5 scales, we may say that initially our reliability was of 2, and then after this resistance reduction, we get a reliability KPI of 3. We can evaluate also on the same inspection the safety KPI of the bridge, and in this case, based on what we saw, there was some cover that could have an impact on the vehicles, but the probability of large shanks to fall down is not so high. But although we identified that this can happen due to spalling, also there was some damaged railings that could jeopardize the traffic safety. And based on that, we also took these tables into consideration from 1 to 5, and we give a KPI value for the safety KPI of 2, which means injury return period of 75 years, or in other words, that it's very unlikely that a person could get injured because of current bridge performance. So then we can pick this framework that I already showed you before, and based on this framework, we can establish the bridge type. We can pick the bridge element that we are in analysis. We can take the information about what material is this element made of, then the year of construction, the collapse mechanism that is connected to each element. So if it is a bending or a shear collapse mechanism, which are the 2 main mechanisms in terms of ultimate limit states, and then in terms of service KPI, or safety KPI, we can evaluate the falling shanks from the deck or the falling of the bridge in terms of the damage on the railings. So for the 2 first KPIs, we can identify also in what vulnerable zones it was identified the pathologies or the damage, what pathologies were identified, And what is the KPI? So the reliability is the first KPI in evaluation. And we checked that the burning failure mode should have a KPI of 3 today and the shear of 2. So from the 2, we use the 3 as a value today for this KPI. And the same for the safety. We evaluate the spalling and the broken railings, and the 2 situations. 2 is the worst one, so we took 2 for the safety KPI. But we need also to address later the component of time. And time is a projection based on the material degradation durability. And we can do this projection for 15 years or for more, which is the number of years that, let's say, the KPI of the reliability KPI or the safety KPI will be maintained on 3 or on 2. In terms of economic and availability, which are the other 2 KPIs that we need to take into consideration in the quality control framework, these are based on the scenarios that we need to address. And also we can classify the availability from 1 to 5 according to these tables, and the same for the costs. Of course, the cost and information from the cost, all classical bridge management systems, they have this information, the unit costs, the mobilization costs, but also the maintenance intervention costs. So all this information is there, and based on that, we can calculate the costs. And then I'm gonna further let you know how we will transform these costs also in a grading from 1 to 5. So this is a resume of the reliability and safety KPI that are coming from the assessment. Then we do the projections, we do the scenarios of interventions, and then we have different costs and availability KPI according to the strategies for maintenance strategies that we are going to implement. So here we have 2 scenarios. We need always to have a reference scenario, which is a comparative scenario. And then in this case, we have another preventative scenario. And in each scenario, in this plot, you have the KPIs that we take into account: reliability, cost, availability, and safety. And for each maintenance scenario, for each maintenance strategy, we have, for the same time horizon, we have different reliability levels and different safety levels and different costs and availability. And then we can compare it one with another. Let's say here that the grading for reliability, availability, and safety is from 1 to 5, while the costs, we have it in absolute costs. We have the costs in million euros. Later, I'm going to say that we are converting these costs also in the same grading from 1 to 5. So, in this case, all KPIs are expressed on a scale from 1 to 5. 1 is the best, 5 is the worst. And I was expressing the costs can come from 0 to the highest cost, which is to build a new bridge. And if it is no cost, we say that the grade is, the scale is 1. If you are speaking about the highest cost to build a new bridge, or rebuild, we are expressing of grading of 5. This way we can draw these 3D plots where we, for the same grading from 1 to 5 and for the 4 KPIs, so safety, availability, reliability, and costs, and for the 2 scenarios, represent the reference scenario and preventative scenarios of maintenance interventions, we can draw these 3D plots. But these 3D plots are very complex and very difficult for us to take decisions. So what we do, we implement the net present value theory in order to convert these KPIs from 1 to 5 into today values. So we need to have the cumulative values in the lifetime analysis and take the decision for us today. So we have to use the same scale from 1 to 5, and then we need to reduce the KPIs to the same scale as for any time instance, the net present value, through the net present value theory. So we divide with net present value, which is calculated if all KPIs were 1 over the whole investigation period. So we divide the scenarios that we have with another scenario with KPI with all the KPIs with a value of 1 during the whole time period of analysis. And this way we can calculate these two plots for today, take into account the net present value theory, and we can compare directly for today the reference with the preventative scenario. And in this case, the scenario that has a larger area, which is a scenario that is close to the KPI values of 1, is the best scenario to choose. So in this case, the preventative scenario is the one that should be chosen in detriment of the reference one. So now I'm going to speak a bit about quality control. You know that decision making is part of this framework, but also I want to integrate it on an asset management level. So in an asset management level, we have the database, we have the performance prediction, we need to have scenarios, and then we need to take decisions. And here is a simple example of a bridge in Portugal. It's an arch bridge. This bridge belongs to Infraestruturas of Portugal. It has 2 inspections in the past and 1 repair work that was done in 2010. And there are some NDT tests. So this is the location of the bridge in the interior of Portugal. It's an arch concrete bridge. And it is, as I said, a simple supported deck arch bridge. And you can see here the main elements of the bridge. So these are, let's say, the main elements: the deck slab, the arch screening, the spandrel wall, and the wall at the beginning. These are the main elements of this bridge. And then we can identify the defects based on inspections. We did the inspection of the bridge, and based on that, we identify some airline cracks, we identified some lynching, we identify some wet spots, and also we don't not only identify, but we also correlate the place where this was identified with the location and the element where these pathologies were identified. So these are more pathologies that were identified, such as efflorescence and vegetation and so on. And these are the vulnerable areas for our bridge. And in this case, we have bending collapse, and you have the high moment and region for bending collapse in red, you can see here. Then you have compressive collapse due to a high compression zone, and you have here also number 2, the other limit state that can happen in this bridge due to high compression level. But also I'm introducing here a service limit state of a deflection, a higher deflection that can happen. These are the pathologies that we identified, and we not only identify the pathologies, but we correlate it with the elements and the location where these pathologies were identified. So it's very important for the inspectors to take the image and also the location and what pathologies are we referring to. Because if we correlate these 2 points, we can check if these pathologies are or not in one vulnerable zone, and what is the mechanism, the limit state function that is connected with each pathology. So is this pathology reducing the resistance part of any of these limit state functions that we have, bending, compression, or deflection, or not? And this comes with the protocol, with the quality control framework procedure that I already told you. We do an analysis for bending, for compression, and also I'm including here the safety KPI. You can see here with S, the last 2 lines. So from the first lines, we have bending and compression failure. And from all the possibilities and all the pathologies and so on, we identified that the most critical is the corrosion that is happening on the walls that is connected with a compression failure mechanism. And then we pick up the reliability of 4. And for the safety, we do the same analysis and pick up a safety of 2. But we can go further. We can calculate also the version reliability. In this case, the version reliability is a reliability without any damage or pathology. In this case, we obtain a value of 4.26. And then, using the same plots, we can estimate the reduction on the resistance due to the inspection and our experience. We identify a reduction of around 8%. And this means, take into account these plots, that our beta initial beta today from this inspection is 4.17. Then we can implement different scenarios, different strategies. In this case, I'm giving you a more analytical procedure for these strategies. One strategy that we assume here as the reference strategy is the no maintenance strategy, but we incorporate also two more, one preventative and one corrective strategy. And also we use this degradation model, this analytical model, for estimating the reliability evolution with time. So based on these two strategies, preventative or corrective, because the first one, the do nothing, is without any maintenance activity. So we split the corrective in corrective actions, so crack sealing, waterproofing, and so on. And we need to include here the effects of each action. And the same, we include here the preventative actions and their effects. That can be a delay on the degradation, can be a reduction on the degradation rate, or can be an immediate improvement on the performance, on the reliability of our bridge. So these are the costs of each corrective and preventive interventions or activities. And this plot shows up the scenarios for the degradation model that we have. It shows up the scenarios, the do nothing scenario. Here, we don't allow the bridge to go to a reliability level lower than 2. So the do nothing is until 2. And then we have also the preventative and the corrective scenarios. And then we establish these grades from 1 to 5 that I already showed you in the table for this collapse mechanism. And we can draw up these scenarios for the lifetime analysis of the bridge. And once you have these scenarios from 1 to 5, the 3 scenarios, for each scenario we have different costs. Of course, on a do nothing scenario, we need to build up a new bridge, so we're gonna achieve the maximum cost, which is to build up a new bridge, so we have a KPI of 5. But also we have the availability scenarios for each do nothing, preventative or corrective scenarios, and also we have the safety KPI scenarios. And using the same procedure, net present value theory, we can convert each grade from 1 to 5 in one value, take into account the interest rate, the discount factor, and from this analysis, we conclude that the corrective maintenance scenario is the right one. So I'm achieving now the last part of my talk. And the last part of my talk is, okay, we did a very good work. We implement a framework for KPIs. We bridge the gap between inspectors that are doing inspection and taking values for the performance indicators, and between the technology, the NDTs and the monitoring that are taking these values with the decision makers that establish the goals and take into account the KPIs that define the best strategies. But what's next? What needs to be done in the future? And this is some analysis that we made. It is an analysis based on all the management systems that are being implemented all over the world. And it's quite interesting to see that a lot of management systems, or almost all, they include bridges, viaducts, and similars, but only a few they are including other asset types. So there is a missing here, which is to incorporate not only bridges, but other transportation infrastructure assets. But also we did in this same study, same analysis, we did another check, which is how many systems include predictive models and optimization models in order to give us the best decision support in terms of the best maintenance strategies. And a lot of them, they already have the deterioration models and optimization models. But let's say that these models, these deterioration predictive models, they are either or analytical, deterministic analytical, or either they are Markov based. And still, nowadays we can say that there are models which are more liable than these ones. And the other thing is with respect to the optimization. The optimization is done in a very by these systems in a very simple approach. they are not using too much complex global optimization algorithms or whatever. They are using simplex methods and so on. So still there are some tools that can be used and implemented on the optimization procedure. And finally, and this is another point, what is also missing here from this analysis? We say that some of the systems they are web-based, some they already integrate the GIS, they use some big data analytics. But if you speak about BIM, virtual reality, augmented reality, and automatic connection with drones, only a few are using this. So what is needed? And what is needed is to use better forecasting performance models, maybe using the artificial intelligence tools for that. We need to incorporate the extreme events, natural and man-made, on the decision-making, on the management, and we need to do that, and I'm going to explain a bit how we should do that. We need to use novel decision supporting systems by implementing global optimization algorithms that will be able to give in a very short time the most suitable decisions and the most efficient decisions. We need to use BIM definitely for the efficient management of our structures. And also we need to go from the system, from the small scale to the larger scale, and also to apply it to other infrastructure types. So if we go to forecasting performance, we have many models that are being used. Some or most of them are deterministic, those that are being used by the current management systems, and some are based on Markov models. Nowadays, there are other models that give us the results with more accuracy. Here is an example of some studies that we did with data from many bridges from all over the world, and based in this case is from the NBI database, but we did it with many other databases. And the fact, and the good fact, is that if you take into account the accuracy factor, the artificial neural networks, which is an artificial intelligence tool, is the one that gives us the best and the more accurate results. And if you take a look into this, the Markov, the traditional Markov, also is not the best one. The hidden Markov gives even better results than the traditional Markov. And this is the main reason for that, is that most of the databases are incomplete, or they do not have enough data, and the Markov doesn't work so well. So in this case, the artificial networks is giving much better results, and this is something that should be for the future and for what's next. The other point is how to include extreme events, and this is some studies also that we made. In this case, we developed under a European project, Horizon 2020 project called Safeway. We developed what we call hazard maps. Hazard maps, in this case, that gives us the dominant hazard that causes the highest transportation infrastructure exposed in each region. And if you can see here, most of the transportation infrastructure, almost 40%, is affected by surface flooding, and 34% is affected by river flooding. So if you speak about other hazards, other natural hazards, their effect is very low. So most of the relevant, the most critical effect here is for transportation infrastructures is flooding. Also, we developed vulnerability maps that we place the exact location, the precise location of the sites where people, natural environment, or property are at risk due to some catastrophic event. And we, based on these vulnerability maps, we can convert them later on in what we call the risk type maps. So this is the risk maps that we also develop, and we came from a larger scale to a more reduced scale. And here is some information about projected changes in the frequency of adverse weather events, so natural extreme events for the transportation infrastructure. You can see that there are some, for each region, we have some events like flooding or droughts or whatever that is affecting more the transportation infrastructures. But then you need to do a small scale analysis. And this is the hazard maps, the consequence maps, and combining hazard and consequence, the risk maps for flood and for a region of analysis here in Portugal of a transportation infrastructure. And once we have these maps, we can identify the most important and relevant extreme events that can happen during the lifetime of our transportation infrastructure, of our bridges, of our tunnels, of our slopes. So how we can, or what should be the next steps? We need to combine the aging that is given by our damage forecasting process, by our deterioration process. So we need to combine the aging with the extreme events that will happen with a probability of occurrence that we need to identify. And also we need to incorporate here the resilience models, which is defined as the ability of societal units to mitigate hazards, these extreme events, and contain the effects of disasters when they occur, and carry out recovery activities in ways that minimize the social disruption, so the availability of and operation of our infrastructure, and mitigate the effects of future earthquakes or any other events. So this is the resilience formulation that we can use. This depends on the time of the shock, on the time that we need to recover after shock. And then we have these functionality curves that we can use more empirical or more analytical recovery functions. And we can also implement more short or long-term recovery models. This depends a lot on the country, on the owner, on the decision making. And this way we can combine, as I mentioned here, we can combine the aging process that gives us the evolution of reliability of the safety and so on. We can combine this with the extreme events effect and the recovery after extreme events. And we did some studies, some tests with different functions to see, and for different countries to see what is the recovering after shock and what is the decreasing on reliability once we have a shock. So we can incorporate both, and this way we can implement and say what is the most optimal strategy in terms of risk mitigation measures. We will not speak about interventions, we will speak about risk mitigation measures that will contain the risk of aging, but also will contain the risk of any of these extreme events to happen. So we can combine the two in the same lifetime period. And this is something that should be in the future. So what's next? The other point is using novel decision supporting system. I spoke about multi-objective with many KPIs. We have these drawings, but now we don't have 1, 2, or 3 scenarios. We have infinite scenarios with many corrosion process, with different processes, with uncertainties, with many intervention types, with many. And what is the best scenario? And for this, we need to define good models, good optimization models, and we need to use good algorithms or strong algorithms. In this case, we have example of evolutionary algorithm that was used with a stock of pre-stressed concrete bridges in order to identify the best strategy in terms of performance, in terms of costs, or in between. And these algorithms, these evolutionary algorithms or others, should be implemented to support the owners to take fast and efficient decisions. Then I spoke about using technology. This is a missing in many infrastructure, but it's a need. And this is some work that we did. We implement the BIM and we convert cloud of points and all the information that we get from on site, we convert into a geometry, and then we include the reinforcement, the pre-stress, and the reinforcement on the BIM model. And this is something that I imagine all of you already did, or some of you. But then also we identify the pathologies with different techniques, visual inspection, NGT, and so on. And we match each pathology So the shared parameters and the parameter time we matched using EFC files, we matched it to the BIM model. So using semantic enrichment and so on, we match it. And this way we can say that in this point, in this location, this vulnerable zone and so on, we have corrosion, we have a crack, we have a whatever. And with that, we can say, and we can recalculate the reliability KPI, and instead of having an estimation of a resistance reduction, we can automatically calculate the resistance reduction and reliability KPI, the exact KPI for our bridge. Finally, the application to large scale and other infrastructure types, which is another thing that needs to be done. We have here an example again of Safeway project where we implement this quality control procedure in a way that we could define for a large stock of bridges in the network what are the vulnerable zones, the version reliability, the identified damage, and then the resistance reduction, and so on. In this case, since we are speaking about a huge amount of bridges, we need to use simplified methods to compute the version reliability, and also we need to use simplified methods for developing the predictive modeling or the reliability evaluation with time. And this is an example of a very simple bridge, a simplified scheme of the bridge, and how reliability is the evolution of reliability with time. And if you do it for all these bridges in a very simplified manner, then we can implement the quality control procedure that I spoke before, but in a very general way. To finalize, we can also extend this framework to other kind of infrastructure types. This is an example of urban systems where we have telecommunication infrastructures, power systems, many other of infrastructure, not only transportation infrastructures. The problem here is a problem of scale. In this case, we combined extreme event, which was fire risk assessment in the historical center with a damage modeling of each of the element that infrastructure element that takes part of this scale of analysis. And then we need to identify what we call as the critical index determination using two procedures, one more qualitative and other more quantitative. And based on this critical index determination, we can define then and take better decisions and better on a large scale analysis. Of course, when we speak in a large scale analysis, we need to integrate this in a GIS platform. This is a need. And this is what we did in the past. And to finalize, this is another project that we just started where we are going to implement the management not of the transportation infrastructure, but to implement the quality control procedure and the management, but of what we call port or harbor infrastructures, which is the GIAP project. And we are combining these also with extreme events, in this case, storms, wind storms, sea storms, and so on. So thank you very much for your attention. I'm now open to any question, and I want to acknowledge all these projects and all that contributed to this talk today. Thank you very much. And now it's time for you to make questions. Thank you very much.
Thank you, Jose, for this very comprehensive and interesting presentation. I encourage all participants to put questions in the Q&A table. It's just on below of the Zoom window, and I will handle them when they appear. But maybe, Jose, I would like to start with the first question, if it's okay. So this process about the quality control framework, is that now, and I'm sure that some structure managers may think that this is a revolution of the existing way of working, you know, with visual inspections and structural assessments and then decision making. Could you elaborate a little bit about this Are there any new skills that is needed from the engineering society or from managers?
Let's say we are, of course, our industry is a bit reluctant to novelties and new technologies and so on. Saying that, the procedure that I present today and that we discussed initially on the cost action 1406, this procedure was intended to be not too far from what is being done, at least in Europe, by the owners on the quality control of their infrastructures. Saying that, I think that it's more a question of readaptation and reusing technologies that are in our hands. Let's give an example of BIM. BIM is something that is already used for designing. So why we cannot use and implement it in the quality control, in the management, and in the decision making? So we are speaking more in the philosophy, a bit change on the philosophy, and a bit change and adjusting on the technology that is already in our hands, rather than to give a big challenge or a big difference in the philosophy. It's more an adaptation, a readjustment, and put all the things that we have in our hands put in the right way. So the inspectors should do the inspection in the right way. The decision makers should do it in the right way, and the technology should be used also in the right way. So in this sense, I think what is really relevant, apart of course of investing and of developing technology and framework and so on, is also to invest on people, on human resources, and also on the training and on the formation of such people.
Yes, and also related to training, we have a question here from the audience. Well, inspectors are not always subjective on their rating. I think we are talking about condition rating now. Is that something that can be handled by the models that you have shown?
Let's say we did some tests during the cost, and after we did some tests we did two types of tests. We did tests that we picked inspectors from different countries, and they did inspection of the same bridge, and the variation was a bit high, because the philosophies are very different from country to country as well. And also in the same country, in the same, and this for me is even worse, in the same owner, different inspectors, they classify the bridges in different ways and giving different grades. And what we need to do here is to make the process more objective, and this is what we did. So when we try to merge what we see with the structural part, we try to put this more objective. And also we need to train, because if we train, that the truth is that at the end, some doubts, and if there is exchange and discussion among the different inspectors, some doubts that one have will be clarified by the other, and other way around. So at the end, if we train and if you use a methodology like this one, which is very practical and at the same time very objective, much more objective than the ones that are being used today, of course, this will make the process more objective. Just to finalize, also, I hadn't time to speak about everything, but we developed and implement some platforms, some apps to be used in tablets. And this could also be interesting, because this could make the process more objective. If you use tablets, if you use the app with all the information, and will allow, the final decision is from the inspector, of course, but will allow the inspector to give a more objective grade and reduce the dispersion among the different inspectors.
In the same line, is it possible to have a harmonized training, or is it every country by its own? Now you have shown the quality control framework. How do you see that? Is that by private organizations? Is it universities? Is it organizations?
Well, I think that each has its own role here. So private companies, they want to make business with this, and they need to have already tested and validated tools. and they need to start implementing and using the more efficient tools as they have in order to be competitive and give a good result, a reliable result, and to support owners. Owners also have their role here because they should accompany the development of these tools by the researchers, by the companies should test. They should allow to do the tests because at the end is for their own use, and they are of course interested that these technologies should be as reliable as possible. And then the academics also have a big role here because many of the points that I raise in what's next, they are being raised by academics, by research projects. And of course, from the moment you start studying a topic, you develop, you validate until you will arrive at TRL that is enough to be commercialized or implemented by an owner, it takes time. It takes 3 years, 4 years as a minimum. And that's the good point of these projects. And that's a good point that the companies and owners should be in line with the universities. So this is one point. The other question is about the different countries and if we could do training that could be transversal to different countries. My experience is if we speak about main topics, yes, it's nice. You can have training that could be more or less transversal to different countries. And we had very recently a very good training with very good results with different countries, but we have others in Prague, in Thessaloniki, you know. But the question here is, at the end, each country has its own philosophy and we cannot change it. So we need to be flexible enough to adapt our tools and our technology to each country. So we can train, yes, we can learn from each other, yes, but at the end the decision is from each country.
Okay. Then I would like to combine two questions that we have got. The first one is whether or not we should continue to do visual inspection, and if not, what else, or what is there a tipping point in the future where they are not more relevant? And also, maybe you can touch upon the different need of data according to the level of assessment that you are doing, and it's also, I guess, bridge type related if we stick to bridges as a structure type. So first, okay, visual inspections, and then what kind of data is in demand?
Yeah, this is a quite interesting questions. So when I show one of my first slides, yeah, I told that our depending, and this comes also from a survey that you made on the cost, our depending from visual inspection, all owners is very, very high. And this is questionable because today we have more and more NDTs and monitoring and drones and so on, which are cheaper. And what I say here is the visual inspection should not be replaced, never. And neither the technician that reads the information provided by the NDTs and by the drones. So the drones are mechanical technology that will allow us to arrive closer to the bridge and do more accurate inspection of more bridges with less time at the end. But the final analysis of the image of the drones and everything, it should be made by an inspector. I tell you a very simple story here where I know that some inspectors, now they become drone pilots. They even get the course because they can install a camera there and they can very easily see the images and go where they want to go. But they have their experience, they have the past experience, which is very important because in order to know where to go, you need to know and you need to have experience from what you are reading. It's the same thing. You cannot put a doctor, expert in X-ray or resonance magnetic or whatever, giving some feedback on a problem in a knee or a problem in a stomach or a problem in a heart. It's not possible. There should be people that should be experts on one thing, manage the technology, another at the end that should be experts on giving. So in resume, I think that the technology is becoming cheaper, and for sure, the percentage of visual inspection going to the bridge and so on, as we know today, will be reduced, but will not be eliminated. Will be reduced, and also will not be eliminated. And also at the end, the final decision, even with NDT and monitoring, it's from the technician, from the structural engineer, or from someone with experience. So this is one point. Maybe reduce how we see today. The way we proceed today may be reduced with a new technology, but at the end, our work will not be replaced, because at the end, the engineers should have a final word. Concerning the level of analysis, I must say that this depends. Of course, most of the standards, they define routine inspections, principal inspections, special inspections, and so on, with some timeline between each of them. And in each of them, we have different levels of analysis. There are some people studying that in FIB. There are some task groups. And the fact at the end is that this is directly related with the risk that each owner wants to take. Or the uncertainty that is able to attain. If there is a limit of a certainty that I cannot afford, then I need to do a more inspection, and maybe I need to do some deep inspection. We are doing some studies in this line with people from Estonia, and with some students, doctoral students from there, and trying to have a more dynamic inspection calendar, which means that the inspection and the technology that we are using should be dependent on the threshold defined by each owner, by the certainty that is able to attain, and the technology that is using. So I must say that should be more, and we need to use the data analytics for that, and should be more and more case-based and not so standard, in my opinion.
Okay, thank you. And then there's another question from the audience about the benefit of applying structural health monitoring sensors in order to early detect failures before they happen. Can you touch upon what are the promising structural monitoring seen from your side, and also do they provide the data needed for decision making?
For sure. Again, I think we need to use the technology, and there are a lot of advancements in structural monitoring, mainly in mechanical engineering and industry engineering. We need to reuse it to the construction engineering. Again, it is a bit, this industry is more reluctant, but you need to use it. And what is promising, I must say that we are getting more and more sensors with more accuracy and cheaper. And I'm speaking, for instance, on the accelerometers. We can have accelerometer, we can implement accelerometers, we can get frequencies, we can get other parameters, and this can be very easily included and incorporated in a quality control framework, and it will allow, of course, owners at the end to take better decisions. Again, after a pre-checking of some expert. And other is the technology from satellite monitoring and so on. So it's a technology that is in our hands. We should use, and there will be very promising sensors with nanotechnology, biosensors, and so on that we need to use for in the near future.
You also touched upon in your presentations that a lot of these input parameters or assessment values, they are uncertain, and often this call for risk-based methodology. Can you share with us some of the issues related to this transition to a risk-based approach, both qualitative and quantitative? I guess it's the managers want stable budgets and transparency, also transparency across assets and across different KPIs. Can you share with us your opinion on risk-based management?
Yes, this is a long story and could be one presentation only about that. The risk base should comes from the moment you do the inspection, you start the inspection until the moment you take decisions. On the inspection side, you need to you start with the risk base, because when you define the vulnerable zones and so on, this is risk base. You are checking the problems and damage in the location which are more critical. So you are doing the risk base in terms of structural side. And then all the KPIs that I identified are risk-based, because let's say reliability is risk-based. If you have a collapse or service problem, then you have consequences, and this is risk-based. Safety is risk-based, because if you have less safety, you can have car accidents, and then you have consequence, risk-based. Costs are risk-based, economy directly, and availability, of course, is also risk-based, because anytime you do an intervention with more or less unavailability, you have consequences on the traffic, on indirect costs, and so on, and this is in risk-based. So all the procedures should be risk-based. It's not difficult to transform the one to another. It's not difficult to do it risk-based. It's a matter of training again, it's a matter of studying, but it's not difficult. At the end, we as engineers, we have a very strong risk-based concept in our hands. We do a lot of decisions, design and so on risk-based. The other thing is qualitative and quantitative. The problem here is how we decide in the cost to start with qualitative approaches, because the truth is that when you speak with large scale, if you go to quantitative approach, or either you have supercomputers, or either you have more simplified models, or either you have BIM technology to support you, or if you don't have, it's much better to do qualitative. But it's always much better to do qualitative risk-based and than what is doing now. So my recommendation is to do as we decide in cost, qualitative and risk-based. Train. I want to put this as a target. Use new technologies, and then when you have a higher amount of investment and so on, or for some specific bridges that are more critical or more special bridges, then you can do a quantitative based approach. But this is my recommendation.
Well, we have one comment here from the audience. Quite a few models can predict the time to crack of concrete structures due to corrosion of reinforcing steel. Should we trust these models by waiting until the time to come out and repair, or how should we use these models? Thank you.
That's a good point. And one of the what's next steps is to try to have better models and more efficient models. The good thing on artificial intelligence models, and also from Markov, is that you are doing and developing a model based on the historical that you have. And if you have, of course, at the end, you're going to say there are not two equal bridges. That's true. But if you clusterize well your bridge by topology, by exposure, and so on, and this is a very important step, you may have tendencies. And once you have tendencies, you start to have predictions. And predictions are what we have, is predictions. Of course, then you can use Bayesian inference tools and so on to update your predictions. But at the end, you have predictions. And it's better to take predictions. At least you have a model and something that will support you, rather than to have nothing, which is done today. So my recommendation is try to invest in good models that should be artificial intelligence based, because you can support them on previous and past data, and based on these models to take decisions, and then update your decisions with the data you get from monitoring, from NDTs, whatever.
Okay, thank you, Jose. I think we would like to wrap up now, and thank you for your excellent response to the questions from the audience. I thank you for your presentation, and I hope you have all enjoyed the webinar and learned a lot from what Jose has just presented. I'm sure that he's happy to take any questions or comments that may appear during the weekend or later at a later stage. We have put José's email at the bottom right of our background, and my email is there as well. If, of course, you can go to the IAPSE website to do further reading of what is going on in Commission 5, and especially also in the working group 5.2 on key performance indicators, chaired by José. I would like to thank you, IAPSE, for support and for hosting this arrangement. And the presentation will be uploaded again on the IAPSE webpage. Go to e-learning, and you will find that alongside the first presentation. And then I would like to do a small promotion for this the coming IAPSE conferences, and I'm just putting them up here on the screen. Hold on. So the future IAPSE events, that is the IAPSE Symposium right around the corner in Wroclaw from the 7th to the 9th of October, and it will be held as an online event. Also, there's a IAPSE conference in Seoul in 2020 from the 9th to the 10th of November. The topic is risk intelligence of infrastructures, and the organizers have stated that it will be a hybrid online-offline conference. Then the IAPSE conference Congress in Christchurch has, as you know, been postponed until February from the 3rd to the 5th, and it will be held as an online Congress. And then finally, there will be a IAPSE Congress in Ghent from the 22nd to the 24th of September. And its theme is structural engineering for future societal needs. It is planned for a combination of on-site and online conference. And you should submit your abstract for the IAPSE Congress in Ghent before 15th of October 2020. And there's a lot of different topics on this sub-themes of this event. So with this, I would like to thank you all again for participating in this webinar, and I wish you a good day or good night or good morning wherever you are. Thank you.
Thank you very much also, Paul, and thank you to IAPSE. See you.